part, oh. So let me put it into words. I'll put it into words. F less than A is subset of the domain of F such that the image is less than A. Okay. Anyway, that is. You're like, I don't have a good intuition for why that should be what's quote unquote a measurable function. Do you? I mean, let me not put those words in your mouth. Can you explain me why this is an interesting definition? So you're saying this is modeled on the notion of topology?
Yes, the continuous function is when inverse image of every set is open.
The inverse image of every measurable set is measurable. So, so if the
Well, I mean, that is kind of very strict definition. I mean, like, if you consider the base measurable set, I don't think you would have an answer. But if you only define like border set, inverse image of border set is measurable.
I'm just thinking about strict analogy to the definition of continuous function in topology at the moment. So there we want that the inverse image of any open set is.
But I think on this one, we can prove that the inverse of any border set is also measurable.
The inverse image of any Borel set is also measurable in this definition, you say? I guess my question is, we're looking at the inverse image of what sets in the range here? I mean, that's not, it doesn't seem to me like that's all possible measurable sets in R. I mean, those are, oh, okay.
Or at least border set.
Oh, my goodness, I have so many things to say. Yes. All right, so, he says, first we note that there are many equivalent definitions of measurable functions. For example, we may instead require that the inverse image of closed intervals be measurable. Indeed, to prove that f is measurable, if and only if I'm going to write down these equations here. That's what I told myself to do if I follow my own advice. So we have f less than or equal to a is the intersection k equals 1 to infinity of this notation, f less than a plus 1 over k. And for the other direction, he says f less than a can also be looked at as the union, k equals 1 to infinity of f less than or equal to a minus 1 over k. Do these make sense to you guys? Notationally?
It's like minus
Ah, oh, okay. So if we take, oh, I see. So we're thinking intersections of a little bit beyond A, a little bit beyond A, a little bit beyond, and getting closer and closer and closer and closer. We close in on including A, but nothing above it. That makes sense. This one, for why. So this is minus infinity less than or equal to f of x less than A, right? I mean, that's, it's, x in E, right? X in the domain such that that condition is met. That's what this means. But the thing is, the measurability plays well with the infinite intersection. So that is, yeah, that is measurable, right? And the other side here, again, it makes sense if you just kind of view it. You're going a little bit, you're not quite getting to A, but you're getting close to it from the other side. And if you take the union, you get closer and closer and closer and closer from the other side, and so it makes sense that it's that. Anyway, he's trying to prove, what's he trying to prove? He says, I'm sorry, I'm getting lost in this particular paragraph. He's trying to explain an alternative definition, right? Oh, so basically we're just quibbling over the fact that you can include A, and it doesn't change anything. Okay, good. Let me try to say some more things here. So he says a simple consequence of our current discussion is that, well, one of the things I probably should write down is that f less than or equal to A is equal to the complement of f greater than A. So that's his notation for complement. I think I would typically write it oh, that's a good question. Where are we? RD, right? Thank you. You're right. It's in the subset of RD. So RD minus. Thank you. That's helpful. So he says that has a simple consequence that minus f is measurable whenever f is measurable. Does that make sense to you? F measurable implies minus f measurable. So you're saying x in E such that fx is less than A is equal to x in E such that f of x, well, minus f of x is greater than A, right? Minus A, thank you. And what's that? I'm not sure this is actually the way it's argued, but What is this? You're saying it's the complement of minus f less than minus a? My head hurts. Just play with the inverse image. So yeah, to show minus f as measurable means that if I go directly from the definition, for all a, okay, well, isn't this just from the definition true? I mean, if this is true for all a, I don't see why I need all this fancy schmancy stuff. I mean, if this is true for all a, and this is literally equal to that, which is this, I need for this set to be measurable for all a, for minus f to be measurable. Give me any, pick b. Any b. Set b equal to minus a. Then, you know, since a is ranging over all possibilities, minus a ranges over all possibilities, how is it minus f is measurable? It's fine, whatever. I'm going on. Okay. Property 1. A finite valued function f is measurable if and only if the inverse image of an open set is measurable for every open set. And if and only if the inverse image of every closed set is also measurable. So, property 1, f finite valued is measurable if and only if f inverse of O is measurable for any open or closed O. All right. Property 2, if f is continuous, on Rd, then f is measurable. Ooh. That's nice. If f is measurable and finite valued, all right, and big V is continuous, then big V composed with f is measurable. And let's see here. So property 3. What's suspiciously missing from this discussion? What might you expect in the place of proposition 2? You give me two measurable functions, yeah? Is the composite of two measurable functions measurable? I mean, I guess that would be hard to make sense of unless we're talking about, functions on reals. I don't know how to compose. Generally, we're looking at functions from RD to R, right? So, not a fair question. But what if we were just looking at real value functions of a real variable? Is the composite of measurable functions measurable? Suppose Fn, n equals 1 to infinity, is a sequence of measurable functions. All right. Then the sup over n of Fnx, the inf over n of Fnx, the lim sup, what's that? What's lim sup? What's that mean? Perhaps some of you thought about this yesterday. Lim inf. I thought it was, oh, maybe I'm thinking of something else. I thought it was like you look at all possible subsequences. Oh. Ah. Multiple ways to define lim sup and lim inf. Okay. Now, he says then these are measurable. What does that mean? Didn't we say measurable was something that you affix to, a set? These don't look like sets. Oh, those are measurable. Those are measurable functions. Oh, you're right. Thank you. Thank you. I was thinking something else. But you're right. That is what is meant here. Property 4. Property 4, if we have a collection of measurable functions, then, and the limit as n goes to infinity of Fnx is equal to f of x, then f is measurable. Ooh, nice. So measurability of a function is maintained in the limit. We have a function that's pointwise, the pointwise limit of a sequence of functions, then measurability is still maintained in the limit function. That's nice. And property 5, property 5 says that if f and g are measurable, then one, integer powers are measurable, and also two, f plus g and also f times g are measurable, provided f and g are finite valued. Now, there's a really neat identity on the next page and a definition I have been itching to get to since we started talking this week. So I'm happy we at least got to this definition, but I don't think we'll fully appreciate it until next time, right? And part of it has to do with, well, this is just a fun formula. F times G, this is a neat formula. 1/4, I feel like I need to make some homework problems about this thing. Look at this thing, this is beautiful. F plus G squared minus F minus G squared. That is nice. I mean, this identity allows him to prove that F times G is measurable if you already know that F plus G and F minus G are measurable, because F times G is just attained by a, combination of those things. And if you already know that the part 1, k equals to 2, you already know square of measurable is measurable, so that's how you get FG for part 2 there. And then that leads me to the definition, which I'll pretty much end with today. Two functions, f and g, are defined on E. Are equal almost everywhere. All right. You're right. F of x equal to g of x almost everywhere, x and E. All right. If the set x and E such that f of x not equal to g of x has measure 0. In other words, the non-coincidence set has measure 0. They mostly coincide. And so he then, property 6 says, if f is measurable and f of x equals to g of x almost everywhere, then g is measurable. So to put it differently, if you have two functions, right, and one of which differs by the other on a set of measure 0, then if one of the functions is measurable, the other is measurable. So since we know that continuous functions are measurable, if you have a function which differs from being continuous on a set of measure 0, it's also measurable. So, where we're going, so the next, he talks about approximation by simple functions and step functions. And it's probably just as well that we didn't get to that today. I think that having that fresh in front of us will help us understand the integration of the next chapter more deeply on the day that we talk about it. It's probably not bad that we didn't quite get to the very end of this chapter, is my rationalization for not getting to where I wanted to get to. But anyway, so ultimately, we're hoping to understand how it is that this Lebesgue integral generalizes the Riemann integral and both recovers things we already know, but then extends a little bit past where we know also. Yeah. So anyway, that's it. I'll see you guys next Friday. You got it.